Alright, we're going to take it easy today because there's quite a few people. Yeah, there's a lot of people out here. Alright, let's take a look on page 382. On Friday, we were starting to represent an integral by looking at how that represents the change in something, the change of an amount, specifically if we're given a rate to work backwards from. And we did a few examples on Friday. We're going to do one more today from the notes, and then we're actually going to take a look at a few of your homework questions just to go over together. Okay, and then tomorrow is going to be a free response day when you're going to be in your little groups. Okay, so on page 382, we're talking about a cylindrical can with a radius of 10 millimeters is used to measure some rainfall. During the first 5 days, 3 millimeters of rainfall has been recorded, so that might be worth noting. The height of the water in the can is modeled by the function S over time, which is measured in millimeters. The rate at which the height of the water is rising is modeled by this function. All right, so let's take a look at the first one. Find the value of the integral of S prime from 10 to 15. Using units, explain what it means. Okay, so let's go ahead and just figure that out using our calculator. We can type in that integral exactly as we see it. Make sure that you're in radian mode because your function is trig. Anybody get it? 11.159. Okay, 11.159. We need units and what that number means. Millimeters. Okay.
How high the water rose from the 10 to 15.
There we go. Okay, the change in height, aka how much it rose, from 10 to 15 days. I like it. We doing good from Friday? It's a big idea what we talked about. Okay, let's check out some more. At the end of the 60-day period, what is the volume of water that has accumulated in the can? All right. Now, they don't really give us a volume equation. Typically, they will on the AP test. This is a cylindrical can. Can we write down the volume of a cylinder? Do we know that? Or what parts of it, at least, off the top of our head? Volume of a cylinder? That's the volume of a cone. You're close. Yeah?
Pi r squared h.
Like it, or love it. Pi r squared h. Okay, so we got to figure out volume, which means we need some type of radius. Do we know the radius of the can? 10, they tell us at the top. All right, and then we need the height of the water at the end of that 60-day period. Now, they don't give us that explicitly, but maybe we can figure it out kind of like how the first question we were able to figure out the change in height. Maybe we can figure out the height after the 60-day period ends using some type of integral, okay? So let's go ahead and think about what the bounds might be. Do they give us some type of point we can use to use, or so that we can label one of those bounds?
60 to 5.
5 to 60. All right, so how'd you know 5 to 60?
It says SAT is measuring millimeters in days for 5 to 60.
Oh, up here?
Yeah.
Okay, so that's one way. You can do 5 to 60. Notice how they give you some beginning point as well. They said during the first 5 days, you had 3 millimeters of rainfall. So if you wanted to label that as S of 5 equals 3, you could. So we're going to integrate S prime. And if we work backwards from S prime, we should get S. And we need to do top minus bottom fundamental theorem. All right. Now you can use your calculator for the left-hand side, just like we did in the first example. Type it in exactly as you see it. Let's see, when you type that into your calculator, I think you should get 163.565. Does that check out? Okay, so we can go ahead and add over this, bless you, we can go ahead and add over the 3. All right, so what does this 166 number represent? That's the height at the end of the 60-day. Okay, the 163 number from the integral is the change in height. So if you're starting with the height of 3 and you have a change in height of 163, then that means you're at 166, some type of ending height. So let's go ahead and use that in our volume equation. So we know the radius was 10. And at the end of the 60-day period, we calculated a height of 166.565. What'd you get for the volume? Kind of a large number. Yep. Millimeters cubed. Good. It's a volume, so we need a cubic unit. We doing okay? All right, let's check out the last one. We're gonna try to do this one by hand. Okay, no calculator. Excuse me, no calculator. This is a completely different problem, so we're not talking about the water or rainfall anymore. The rate at which people enter an auditorium for a concert is modeled by the following equation for time 0 to 2 hours, and the rate is measured in people per hour. VIP tickets were sold to 100 people who are already in the auditorium when the doors open. So I guess they were allowed to kind of come in early before the general crowd got in. And the doors close at the beginning of the concert 2 hours later. If all of the VIP ticket holders stayed for the start of the concert, how many people are in the auditorium when the concert begins? Okay, so you have 100 already in there. What do we need to calculate to figure out how many are in there when the concert begins?
R of 2.
Say it again?
R of 2.
So if you plug in 2, you'd be calculating the rate at which people come in at the 2-hour mark. If you start with 100 and you're trying to figure out how many people are there at the beginning of the concert, what do you need to figure out to do that? Yeah.
Use the integral.
You need to figure out how many more people entered, right? Some type of change in rate. All right, so let's go ahead and do an integral. So we're going to have the integral of 1,380 t squared What about the bounds? Zero to 2. Okay, so let's go ahead and try to work this one out by hand. Okay, antiderivative using some calculus. Using kind of your reverse power rule, if we were to add 1 to the power, that would give us a t cubed. And then we have to take the coefficient divided by the new power. So it might take us a little time, but we need 1,380 divided by 3. I think you'll get 460. All right. Do you know what? We may need our calculator in a little bit, so I'll let you use it to help you with some calculations, but I don't want you to use the integral command. Okay? So don't go that, I don't want to say cheating route because it is a quicker route, but try not to use the integral command. So let's do the next one. If we add 1 to the power, that would be t to the 4th. And then you got to divide the coefficient by that new power. So 675 divided by 4. You get 168.75. Okay. We know the bounds, so we'll throw in the bracket and we'll do 0 to 2. Which bound do we plug in first? 2, top minus bottom. All right, so go ahead and plug in 2 for all those t's and see what you get. I. Thank you. Let's see, did you get 980? Yeah, when you plugged in 2? Alright, so then we have to subtract what we get when we plug in 0. But hopefully we realize both of those terms have a t in them, so plugging in 0 would just result in 0 anyway. So we get 980. What does that number mean? Yeah.
It's the change from 0 to 2.
Change in what from 0 to 2?
Change in amount of people.
Change in people. Right, change in people from 0 to 2 hours. Okay, so the question is, how many people are in the auditorium when the concert begins? Okay, like how many total people? So if we know the beginning amount and we know the change amount, what do we got to do to those to get the total amount? Add them, right? So we started with 100. We had a change of 980. So that would be 180 or 1,080 people. There's your total. Alright, so an integral represents a change in amount of something, whatever unit you're talking about. It could be rainwater, it could be people. From other examples, I think we had temperature. Okay, so it could be a change in whatever context you're talking about. We're going to keep that in mind when we go to the free response question from your homework. Okay, so let's go ahead and take a look on page 384. Alright, so free response day tomorrow. We might see a question very similar to this, but this one's actually from your homework. So we have a tide that's removing sand. Might not be a good idea to kind of label this. So we're removing or losing sand from a beach at this particular rate. And a pumping station adds sand to the beach at this rate, given by a different equation. Sometimes I like to kind of write down little things to help me remember. If you're losing something, you're normally subtracting it, and if you're adding something, well, you'll be adding it. Okay, so might not be a bad idea to write those down just so you don't get confused later on. Both of those equations are in units of cubic yards per hour, and T is in hours from 0 to 6 hours. At time 0, the beach contains 2,500 cubic yards of sand. So maybe we'll label this as a starting amount. All right, let's check out the first question. How much sand will the tide remove from the beach during the 6-hour period? We have the rate at which it's being removed. So what can we do with that rate to figure out how much? An amount. Integral, we're going to work backwards, okay? So we need the integral of 2 plus 5 sine of 4 pi t over 25. We're looking for the 6-hour time period. So we'll go from 0 to 6. And from there, we'll utilize our calculator. Again, make sure you're in radian mode because we're working with trig. Let's see, can we get 31.816? Yeah. What about units? Yards cubed, yep, a volume unit. They tell us that the functions have units of cubic yards per hour, so we'll use that cubic yard unit. Good. All right, let's check out B. Write an expression for y of t, which represents the total number of cubic yards of sand at any time t. All right. So if you're trying to find a total, let's just think about this in words first, okay? And then we'll try to convert the words to math. If you're trying to find a total, and you have a starting amount, and you have certain rates at which you're adding or subtracting, how can we kind of combine all that information to eventually get our total? Can you kind of say in words what that might look like?
Amount subtracted plus whole starting
Okay.
minus the amount subtracted plus the amount added.
Does that make sense? Like in your head? And if you're trying to figure out a total, you got to take how much you're starting with minus how much you're losing, but then you got to add how much you're gaining, and that'll give you some ending result representing your total. So let's take those words and we'll try to convert them into math or calculus notation. So they tell us that y of t should represent the total number of cubic yards. So on this side we'll have y of t to represent the total. Do we know a starting amount of sand that was on that beach? That was 2,500, right? And then we need to subtract the amount of sand that we lose. How can we calculate that? What do you think, Joseph?
Integral a to b, r.
R of t. Okay, so they give us the rate up top at which we're losing sand, but we'd have to integrate that to figure out how much we actually lost. Okay, the change in amount of sand. So we'll go ahead and do integral of r of t here. Okay, now Joseph said bounds were from a to b. They want us to figure out, let's see, write an expression for the total number of cubic yards on the beach at time t. Let's see. So they're not actually giving us at time 4, at time 5, something like that. Notice how the lower bound should be 0 because that's representing the time that you're starting. But if you don't know the time that you're ending, what do you think we're going to write as the upper bound? T, right. Whatever time you're trying to figure out, that's what we could substitute in for that upper bound. Let's go ahead and try the last one. We now have to add the amount of sand that's being added to the beach. They give us the rate at which it's being added, so we'd have to integrate that to figure out the amount. And again, it'd be from 0 to t, and we'll just say S of t. I'm hoping that the wording to us makes sense, but then converting it to the math also makes sense, going between the two. Okay, so let's go ahead and try C. Find the rate at which the total amount of sand on the beach is changing at time 4. How do you think we can do that? It's asking us about a rate. Do we know any other information about rates? Both of these, right? This is the rate at which we're losing sand, and this is the rate at which we are adding sand. And they specifically want time 4. So let's see, if we can figure out the rate at which it's being lost and the rate at which it's being added, maybe that would give us the total rate in the end. Notice how we don't necessarily need the starting amount because we're not talking about total number of cubic yards of sand. We're talking about a rate, something different than an amount. Okay, so let's go ahead and we can take the rate at which we're being, let's see, added, and then we'll subtract the rate at which it's being lost. Sorry, you can't see that. And we'll plug in 4 because that's the specific time that they're asking us for. So we don't really have to do any derivative or any integral for this case. We're simply going to plug in 4 into those two equations and subtract them to figure out the rate in the end. What'd you get on your calculator? Just to double check so we're all on the same page. Alright, and then what about units? This is a rate. There we go. Yards cubed per hour. Perfect. Alright, so at time 4, the hour 4 mark, that's the rate at which the sand or sand amount is changing. And notice how it's negative, so you must be losing sand at that particular moment in time. Makes sense? Let's try D. So for time 0 to 6, at what time t is the amount of sand on the beach a minimum? And what is that minimum value? Alright, so let's see. In order to figure out a minimum, we know that a derivative, aka a rate, must be 0, and specifically changing from decreasing to increasing or negative to positive. Notice how for part C, we use the S function minus the R function to represent a rate, aka a derivative. So what if we were to analyze when the S function minus the R function equaled 0? We're essentially trying to find a critical point. Now we might have to use our calculator for that because the functions S and R are pretty intense. So what I would do is graph S of t minus R of t in y1. You can graph 0 in y2 and try to figure out where that critical point might be located. Alright, so I'll do that up here with you guys. Since S of t is a fraction, make sure you put essentially the bottom in parentheses because there's two terms. And we have to subtract R of t, but since R of t is two terms, you're going to have to subtract both terms, almost like distributing in that minus sign. So we'll have minus 2 minus 5 sine of 4 pi t over 25. Maybe change your window from -10 to +10. You can always go back and change it to something else if you need to. Actually, we could probably change the window, at least on the x-axis, from 0 to 6, because that's the bounds that they give us in the beginning problem at the top. Alright, so can you kind of describe on that graph where we should be looking? What should we be identifying? If we're looking for a minimum. Remember, this is the graph of a rate, aka derivative.
Where it intersects the x-axis.
Right, so it kind of looks like it gets really close here, but it actually stays beneath it the whole time if you pay close attention to how the calculator graphs it. But we do have a minimum here because the rate is 0, and notice how it changes negative to positive, meaning you're decreasing to increasing, creating that minimum point. So let's go ahead and we can do the 0 command or the intersect command, whichever one you're more comfortable with, to figure out that point. So it looks like 5.112, we'll say. Or sorry, 5.118. Okay, so this is a critical point. That's where a minimum is located, but they're asking us to figure out what is the amount of sand, or what is the minimum value, almost like the absolute minimum, the lowest it goes, even though it doesn't use that word absolute. So now that we know where a minimum is located, how can we test to see if it is the lowest? How can we figure out the lowest amount of sand? Did we already have something on our paper that could help us figure out an amount of sand at any time? Part B, right? That's the total amount of sand at any time we want. Now, we know at time 5.118, there's a low point, but we got to check to see if it's the lowest. So let's go ahead and plug in 5.118 in for those t-bounds at the top. Might take a little time because, again, you got to utilize your calculator, but it should be pretty easy just to type things in and hit enter. Alright, so I know it's a lot to type in, but you want to type in 2500 minus the integral from 0 to 5.118 of the r function plus the integral from 0 to 5.118 of the s function, and that should give you the total amount of sand at that point in time. Anybody close? 2000, go ahead.
492.
Yep.
Oh, wait, 360.
I'll take it. 369, I had 349, pretty darn close. Okay? So that's the amount of sand at a minimum point during this interval from 0 to 6 seconds. But should we check some other points in time? Where else can an absolute max or min happen? Does the extreme value theorem sound familiar? Have we heard that before? Extreme value theorem, I think you guys went over it with Mr. C. All right, so the extreme value theorem tells us that we can have an extreme point, okay, an absolute max or min at the endpoints as well. You got to test those, because this is only giving us a critical point in between those 2 points in time. Let's check out the other ones. Okay, so we got to check time 0 and time 6. Do we already know the total amount of sand at time 0 when we started? That was 2,500, right? So notice how the starting amount is actually more than what you had here, which is okay because we're looking for a minimum anyway. Let's check y of 6. Okay, so go back to your part B equation. We're going to plug in 6 for those upper bounds. So we get the total at time 6.
2,493. 277.
277. All right, so looks like we're looking for the minimum amount, and just by, what is it, 1 cubic yard almost, looks like 5.118 is your lowest. All right, so the extreme value theorem, not only do you have to test the critical point or points that you find, but if you have endpoints, you got to check those as well. Notice how at time 6 that endpoint was almost the absolute minimum. Pretty darn close. Okay? We'll go ahead and try some more free response questions tomorrow.